People coming in.
Hello.
How's it going?
How are you? With you?
Pretty good. Been, it's raining here the last couple of days. It's finally sunny.
Yeah, everywhere.
Hello, Michael.
Good afternoon.
Afternoon.
James Bond is dead. How can we go on?
Yeah, really. And he made it. He had a long run. Amazing, make it to that.
Well, he was the first one. So, do you know who the fourth James Bond was?
No.
He was Australian.
Really?
I have a personal connection to him. I dated his cousin, who's an American, by the way.
Huh? Wait, what Bond movie was he in?
Yeah, good question. He was in only one. George Lazenby.
Yeah, I remember the
I
name.
fell over him. Yeah, have you ever heard of him?
Yeah, totally.
He has an American cousin, Deborah Lazenby.
Debbie.
She's like a third cousin. Otherwise, I would never have heard of him. And she's a descendant of one of the signers. She's a descendant of John Randolph of Virginia. But her politics, I believe, is much different. Oh, you didn't like my comment about the article. Oh, by the by, I just got an email about 2 minutes ago from Barry McFarland, who hardly never agrees with me. He agreed with me on the article.
Okay.
He said it's conjecture built on conjecture built on conjecture, which is basically what I thought.
Well, yeah, I mean, no one denied. I mean, even in the article, they talked about, that, like, there's a lot of steps and things being assumed and it's a lot of moving parts. But it is interesting that so many groups were arriving at similar results from different directions,
Really?
Interesting.
But no empirical evidence. Where's the lab experiment they're talking about?
Yeah. Sure. Well, I mean, so, I don't want to get too bogged down in the wormhole stuff. So I want to do the symmetric qubit stuff first. But I will say, it's like the model that I showed last time, like the SYK model. Like you could run that on a quantum computer, like in the sense that, there's like a translation between fermionic operators and qubit operators. So you could sort of like reconfigure it, run that on your quantum computer. I didn't do that because I just figured, there's like not that many qubits and like it's kind of unreliable, like not really worth it. But the big thing that they were talking about, like that we didn't really do was, we talked about like the thermofield double state, which at infinite temperature is this like maximally entangled state. And then like at lower temperature, it's like not. And like the idea was like basically like take such a construction, I guess, and couple it to a bath so that the temperature lowers and it's kind of like interacting with this some like environment basically. And then it seems like that's the form that they were doing a lot of these investigations. So like as this black holes coupled to this bath.
Can I ask, did you read any of the papers they referenced? They reference Marloff's paper, but there's no link to it. Do you know which paper they're talking about?
No, I don't recall. I've read some.
Barry said he couldn't find it either, and he's usually pretty good at this.
Yeah. That's a good question. I'm not sure. I definitely did not follow up on all the references. I read some of the things that they talked about, and with not like great understanding.
But has anybody even simulated a wormhole on a quantum computer? I mean,
well, like I say,
where's the simulation?
We got an effect, there was some kind of transfer information. I mean, we only use, I forget, like 4 or 5 fermions, on the one side and on the other side. But yeah, it's like that's a concrete enough model of like some kind of information transfer happening. But in a way, it's not that different from quantum teleportation. So you're right to question, the interpretation, right? It's like it's clear you can get this kind of, effect from the outside, something like pop, goes in here, pops out there. But and even in the paper they talk about like just because there is that information transfer doesn't mean there's going to be like some kind of semi-classical wormhole geometry that you can reconstruct. They like mentioned that a little bit. So
no, but teleportation has been implemented. It is implemented.
It did teleport, yeah.
But I mean, they're talking about possibly doing an experiment. They shouldn't even be allowed to publish a paper until they've done the experiment.
Well, that's like kind of a high bar for entry. I mean,
no, I'm saying
everyone's going to know what to look for.
No, a reputable physics journal. Some of the greatest physicists of the 20th century had their papers rejected because it was too outlandish, and then later proven to be correct. But until there's some empirical evidence, this is all nonsense.
We'll get there.
And they're using mathematical tricks to prove something. Teleportation has been implemented. It's basically standard now.
Yeah, and then I don't follow like all the arguments, but like it is sort of, so far as I understand it, it's like in this, quantum gravity path integral, they're like including these like more wormhole looking geometries, and that's sort of like how they get these different results for the black hole entropy and stuff.
And they can't implement it with gates?
Well, it's like,
I don't know. I don't know enough about it.
In theory, you can implement anything with gates, but what are you going to do? You got like 15 qubits.
Well, 15 qubits. They have, up to 53 qubit computers now. Maybe probably higher, but 53 that they're admitting to.
So speaking of, check out the old IBM system here. So I'm going to do something similar to something I did a couple weeks ago. Like I'm going to submit a job to the IBM, one of these computers, and it'll take like 20 minutes or something to come back. So we'll have it here waiting for us. In fact, I'm going to do 2 of them. So I'm not going to explain exactly what this is just yet, but we'll come around. Get that going.
Has a lot of parentheses.
It has a lot of the parentheses. And let's do this one.
Parenthetically,
Yeah.
Where's Moshe? Didn't he say? I thought he was going to show up.
I don't know. He didn't RSVP. Maybe he's busy.
He's going to prove tomorrow that tachyons exist.
Oh.
And all you need to know is Schrodinger's equation and E equals MC squared.
Which, he's a surprisingly ambitious guy, Okay. So, today I wanted to talk about, we've talked a lot about, this topic that's like near and dear to my heart. It's like sort of Majorana star way of thinking about spin. And, today we're going to talk about how to, kind of use it to prepare permutation symmetric multi-qubit states on an actual quantum computer. So you can all see my screen. I hope, is this big enough to read?
It's fine.
Okay, cool. So just like a brief, review of this whole sort of formalism. So like, say we have like a spin 3 half state. It's going to be 4-dimensional, and we can sort of write it out in the JM basis. Here's our different JM basis states, and we got A, B, C, D are the 4 components. But we've also seen how we can also represent it as a state of 3 symmetrized qubits. In other words, if we look at the basis states for the permutation symmetric states of 3 qubits, there are 4 of them. And, there's exactly 4 basis states for spin 3 halves. So, we got this one, which is like they're all up. This is a superposition of the ones with like 2 up and 1 down. This is a superposition of the ones that are like 2 down, 1 up. And then we got all down. And so, and this is general. It's a sort of a counting argument. There's like a 1-to-1 correspondence between JM basis states and, the basis states of symmetrized qubits. So, what that means is we can, that we can form like a linear map that can sort of translate back and forth. We just sort of pair up the basis states. This is just sort of some, actually, I should rewrite this. It's kind of ugly looking. Suppose we take, spin 3 halves. We generate, a random spin state. It's 4-dimensional. And we, apply this linear map to it. And, it's just as, all it really does is it just like takes these 4 components, and just like sticks them in here. And that's, its effect. And so we get this state. And we can check that, this transformation that we made is like an isometry. So if we take S dag times S, it just gives us like the identity matrix. And so it means, we can go back and forth, and it's basically just go back and forth to your heart's content. So, another way of obtaining that result is to work with the Majorana polynomial. So, we can associate this polynomial to a spin J state, find its roots lie on the complex plane, stereographically project to the sphere. We could then, create a bunch of qubits whose, rotation axes, expected rotation axes are like pointed in those directions, and then symmetrize those qubits. In other words, tensor them together in all possible orders and add it up and normalize. And if we do that, we're going to lose the overall phase of the original spin, but whatever. So, just for reference, again, pulling it out from a previous meeting, here's the Majorana polynomial. These A's are the components of the JM state. Z is this like, complex variable. And, it's just basically the components, but you just have this like little normalization factor. And you also have this sign term here, which, if you think about it, comes from, we went over it before, it's like, if you want like a monomial whose root is like the star, or the direction that corresponds to the ratio between the components of your qubit, then you got to add a minus sign. Anyway, and then there's like this little rule that, if we have like a d-dimensional spin vector, but we end up with a less than d degree polynomial, we should add a root at infinity for each missing degree. And so, we're always going to get the right number of points that way. So then, having obtained those roots, some of which may be infinity, we stereographically project them to the sphere, and, I like to call them stars. So here, just for review, here's some code that takes a spin, finds its stars, converts them into qubits, symmetrizes the qubits, and then we apply, the inverse of this transformation we constructed up here to, get back a spin state, find the stars again, and just like check, sanity check. Does this preserve the stars? So, this is some code here. It takes like a bunch of qubits and symmetrizes them. In other words, for each possible permutation of the qubits, we tensor them in that order and normalize. Here is, the code, which it's like hidden away in a little module I wrote, but converts a spin into, the XYZ points, and then we create a qubit for each one of those. Technically, you know, we could just grab the roots and then go right to the qubit states, because recall that those roots are supposed to be the ratios between the two components of the qubit. But in any case, we get our qubits, we symmetrize them, and then we, like, you know, downgrade that symmetrized state to a spin state, and then find the stars again, and you see, you know, the XYZ points that we started out with are the same as the ones that we end with. So this is just sort of some throat clearing, just some review of this way of thinking about higher spin states. So, you know, another way of saying all this is that if we have a state of 2J separable qubits, each with an XYZ point representing its expected rotation axis, if we permute the qubits in all possible orders and add up those permuted states, then of course that state's going to be, you know, permutation symmetric, but also, you know, perhaps remarkably, preserves that information, preserves those XYZ points. And this is like a good example of like a holographic representation, in the sense that each of those XYZ points is encoded, you know, not individually in each of the qubits like they were before, but instead holistically in the entanglement between all of these qubits together. If we then, you know, transform from those symmetrized qubits back, you know, to a spin J state, find the roots of the Majorana polynomial, we can get back the XYZ points. And in that case, we could think about it like we're throwing out the phases of the individual spins, the original spin halves, the original qubits. So, you know, that's all stuff we've talked about before. But, you know, one thing we didn't really emphasize before is that, you know, it might concern you that this operation of symmetrizing like a bunch of qubits is not like a unitary operation, right? I have to make a copy that corresponds to each possible permutation, you know, and then like add them up. And I can't make copies of quantum states. That would violate no cloning principle. So you might wonder, you know, suppose I have 2J separable qubits loaded into my quantum computer, and I want to prepare the permutation symmetric state that, you know, corresponds to them. How do I do it? No deterministic, you know, in the sense of just like a unitary operation will do the trick. But, you know, it's a classic thing in this quantum game, which you can't do deterministically, one can often do probabilistically. Oh, look, Moshe has been waiting. I should have seen that. Okay, he's coming in. So basically, that's what we're gonna talk about. You know, what's a sort of probabilistic quantum algorithm for symmetrizing a bunch of qubits? So we're gonna start just with 2 qubits, because this is sort of simplest example. So, you know, consider like this following circuit here. We're gonna what we're gonna do is we're gonna symmetrize psi and phi, and we got this sort of control qubit here that just sort of starts in the 0 state, or the up state. And go along, we first apply it like a Hadamard, you know, to this state, which, you know, takes the up state to an even superposition of up and down, AKA it's pointed in the x direction. I'm going to come back to these 2 little phase gates here. But, you know, kind of the heart and soul of this circuit is this guy here, controlled swap. This is going to be like recurring theme here. So it's also called the Fredkin gate, after kind of mid 20th century computer scientist Fredkin, who, you know, originally was thinking about it in the context of classical computation. But in any case, you know, I mean, we all know about C0, right? C0, you take 2 qubits, one's a control, one's a target. If the control's up, you like leave it alone, leave the other qubit alone. But if the control is down, then you apply X, or the NOT gate, to the target qubit. So control swap is like basically like the same kind of idea. If, you know, this guy is just like in the up state, you know, nothing happens, but if he's down, then we swap the two other qubits. Controlled swap. So we hit the control with a Hadamard, do a controlled swap, and then hit the control with another Hadamard, which basically like undoes this like sort of rotation that we did at the beginning, but of course doesn't change the entanglement between the control and the targets because it only acts on this top guy here. So, you know, just for sort of concreteness sake, you wonder about this Fredkin gate, this controlled swap gate. Here's a little matrix representation of it. And if you eyeball it, you're like, okay, it sort of makes sense, right? Because you got up here this block, which is just the identity matrix, 4x4 identity matrix. And then down here is just a little swap gate. That's the normal, the usual everyday swap gate. So, you know, that's actually if you don't know this, it's nice, you know, it's a general rule for constructing controlled gates. You know, just take the gate that you want to be controlled like by the first qubit and like stick a identity matrix of like the same size, you know, along the diagonal. So yes, okay, so we got two qubits. We want to symmetrize and a control. Control starts in the up state, apply Hadamard to the control, which takes it to an even superposition of being up and down. So then, right, like when we apply the controlled swap, the two qubits end up in a superposition of being swapped and not being swapped relative to the control. We then apply a Hadamard again to the control. By the way, you know, technically you want to sort of apply the inverse, but Hadamard is its own inverse to, you know, undo the original rotation while leaving it entangled with the two qubits. Okay. Then finally, you know, the sort of climax of the whole thing is you measure the control qubit. And if you get up, then the two qubits end up as desired in this permutation symmetric state. On the other hand, if you get down, then, you know, it's kind of interesting. Our two qubits end up in the anti-symmetric state. So what we want is the symmetric state. I mean, maybe you care about the anti-symmetric state too, but today we just want the symmetric state. And so all you got to do is just keep doing your experiment over and over again until you get the answer that you want. You know, in this circuit here, there's also these two phase gates. And, you know, this was just a point that, like, where the paper that I stole this diagram from was making, which I've included down at the bottom of this whole little essay, which, by the way, I should have said, just remind you all, you know, just if you want to follow along at home, you can find all these notes right here on the heyredhat.github. So, you know, what were those little phase rotation gates? Like, suppose you wanted a state of the form, like it's like a permutation symmetric state, but like there's just like some arbitrary phase factor here. You could get that by adding these two guys for some value of theta. And, you know, if theta is 0, this just reduces to two identity matrices. And then, you know, everything reduces to what I've been saying. So let's check it out. I just, you know, implemented it very, you know, concretely using, you know, Q-tip. Here's our Hadamard. Here's our swap gate. Make a little control swap gate. Here's the phases, phase gates, just set theta to 0. And then here's kind of like the circuit, you know, Hadamard. By the end of this, we'll have implemented it in Qiskit, IBM's framework, and like be able to visualize the circuit and, like, you know, run it on the actual quantum computer. But for now, let's just, you know, do it by hand, basically. It's always good to like kind of see, right? So, you know, here's the Hadamard, here's that first phase gate, here's the C swap, other phase gate, and then the other Hadamard. We take here's our control qubit. Here's the two qubits to be symmetrized. You know, just start off in some random state. Tensor it all up. Here's like a little, just little function that just implements the measurement. You know, just basically takes the partial trace of the control. You know, the probabilities for Z measurement are just going to be the, you know, terms along the diagonal of this density matrix. And we flip a coin, pick one, and then we project the state. So, you know, here we like apply this circuit to the state, measure the control guy, take a partial trace over the two qubits, just throw out the control, and we compare it to the correct state. We know the correct state, it's just this one, A tensor B plus B tensor A. Here's the correct anti-symmetric state, and we just do the comparison. So here you just see, you know, for the given two like random qubits we started out with, you know, you can see here the probabilities for like, by after the circuit's been run, you know, what are the probabilities for the control to be up or down, and then like the result that we got, and then like, yes, it's true that we ended up in the symmetrized state, or come on, give me an anti-symmetrized one. Could do this all day. Look at that. What are the chances, guys? There you go. Well, I guess we know the chances, right? Well, okay. So
These random number generators have to be started up and fired for a while before they really work right.
yeah, right. So cool. So all right. So we've seen basically, you know, what we want to do in the case of 2 qubits. But what if we have, you know, n qubits? What do we do? So like the simplest thing to do is a really like a natural generalization of the above. So, you know, suppose we have n qubits. There's going to be n factorial possible permutations. So, you know, stands to reason, we might want to use a control qubit that lives in n factorial dimensions. So, you know, for 3 qubits, there's 6 possible permutations. So we want a control state that's 6-dimensional. We're gonna, you know, do it this way here, and like after this, we're gonna like redo it again where we use like several control qubits instead of 1 control qubit. So hold your horses if you're worried about that. So, okay, so if we have, you know, 3 qubits, we need a 6-dimensional control state. So as before, you know, we start like with the control in the 0 state, and, you know, basically apply like the Hadamard gate or like whatever. I actually don't know if people refer to it as a Hadamard gate in this context or just straight up as the quantum Fourier transform, which is like what it is. Which you can get like in any dimension. So we form quantum Fourier transform. I'll show you, you know, if you go on the, if you're interested in the components, I explicitly build the matrix down there in the code, but, you know, they have it just sort of like laid out here. Where omega is a root of unity, 2 pi I over n, where n is the dimension of the whole shebang here. So, you know, it just does like a Fourier transform. So for our purposes, this is great because what we want is a gate that takes the 0 state to an even superposition of all the basis states, and that's what that does. So then afterwards, just sort of generalizing the case from before, we want to do some kind of controlled operation, right? Kind of like, but it's not just going to be a controlled swap, some kind of like controlled permutation. We want something where like doing, you know, the ith permutation on the n qubits depends on the control being in the ith basis state. And so if we apply such a gate, then we'd end up with the n qubits being in a superposition of being permuted in all possible ways relative to the control. Then similarly to the previous, you know, algorithm, we apply the inverse quantum Fourier transform to the control and then measure the control. And if we end up back in the 0 state, then the n qubits are going to be in the permutation symmetric state. So how do you construct like such a controlled permutation gate? So, you know, you can just sort of like write it out explicitly like in bracket notation. So what you want is to like sum over all the permutations of your qubits. And then you also want to like sum over all the basis states of the qubits. So here, I labels both a basis state of the control, which would be this, and also pi, which is like the ith permutation, like, and the ith permutation gate that like applies that permutation to the qubits. Meanwhile, you have here j, which labels the 2 to the n basis states of the n qubits. So, you know, you can see like that, like if this operator acts on a guy, you know, coming in on the right, forms a little bracket with this part, and it's going to perform the ith permutation on the qubits to the extent that, you know, the control is in the ith state. So, you know, you could use that to construct it. So here's some code. This is just like a little helper function that constructs, you know, a matrix, a gate, an operator that, implements a desired permutation on some number of qubits. You know, so like if you had, you know, 3 qubits, you'd give it something like, you know, 210, and then it would construct the gate that does that permutation of 0, 1, 2. You know, just sort of proceeds in the obvious way. Just a permutation gate, you know, here we construct the quantum Fourier transform, just what we saw before on the Wikipedia page. And here, this constructs the controlled permutation gate. And it is just, you know, quite literally a translation into code of this. You know, so, you know, sum over the permutation, sum over the basis states of the qubits, and, you know, whatever. Get each term, add them up. Maybe there's a more efficient way of generating it, but I just did it that way. So, you know, suppose n is 3. We find the number of permutations, generate 3 qubits, construct the QFT, construct the controlled permutation gate, you know, construct a projector onto all of the controls, or just, sorry, onto the control. This is the projector onto the sort of the 0 state of the control. And tensor the control in the 0 state to the qubits, apply quantum Fourier transform to the state, control permutation, and then the inverse, and then, you know, project the state into its 0 state, where, you know, I just, like, before I did the thing where I like calculate the probabilities and like flipped a coin or whatever, just out of laziness, I just like project the state regardless of probabilities. Okay, and then, you know, take the partial trace to throw out the control. Then, you know, just to like make sure this is working, we take those original qubits, symmetrize them, find the, you know, the density matrix, and compare them. And computer says everything works, so must be true. Okay. Does that make sense so far? Let me know if there's any questions or concerns. So, okay, so that's great. You know, that's cool. And, you know, like, for example, like I'm working with, you know, this quantum machine learning library, Penny Lane. And, you know, one of the things that they let you do is kind of mix qubit-based stuff with harmonic oscillator type stuff. now. I applied to Xanadu's like beta program to use their photonic, quantum computer, and they haven't gotten back to me yet. But in theory, should that come through, could be playing around with oscillators all day. So, you could do that here in this case. I mean, in a way, it's just, use, some oscillator to be your control, and then, can use that to, condition the permutations of your qubits. But in general, most of what people have are systems that are like entirely qubit based. And so it's always good to formulate everything just solely in terms of qubits. So, so what can we do? And, I'm basically following this paper by these folks here. And, I have to say, it's like a great little paper, in the sense that, it's one of these classic sort of quantum computing papers from the 1990s. And, the actual quantum computers are, like a ways off, but, they're writing like as if they exist. Like, well, if I had a qubit, this is what I would do to it. And, they laid out like basically these algorithms there, a long time ago. And I'll circle back around to it in a sense, because they, offer this algorithm in like the context of doing sort of a kind of sort of a technique for, correcting errors in a quantum computation. So I'll circle back around to this, talk about like what they even wanted to use the algorithm for. But in any case, the basic idea is relatively simple. It's just that, like a permutation naturally can be broken down into a series of just like swaps. And so, just concretely think about it like, you start with some element A, pop an element B to the right, and then perform the two possible permutations, the identity and just like the swap. Okay. Those are the two possible permutations of two elements. Pop another element, C, to the right, like in each of these cases. And then do all possible swaps of C and like the other two guys. So this one, we get, ABC, CBA, and ACB. So you see, these are all the ones where it's just C like appears. Just sort of swap C with each of the ones in turn. And naturally, there's going to be three of them, and there's like three guys here. Okay. And you do the same for BAC, cha-cha-cha. And then, these are the 6 permutations of 3 elements. Pop another element, D, to the right. And then swap D with each of the 3 guys that you had in turn. And then, you do that in each of these 6 cases, and you get the 24 possible permutations of 4 elements. Okay, so this is sort of what we're going to use basically in this quantum circuit, although there's like a kind of an interesting twist to it, as we'll see. So, but that's basically the motivation. We sort of want to translate this idea into a quantum circuit where, we're controlling, basically individual swaps with qubits instead of controlling the permutations like overall with like a single qubit whose dimensionality is, the number of qubits factorial. So first we gotta like prepare our control qubits. So what do we want to do in this context? Before we just use the quantum Fourier transform to go from the 0 state to like an even superposition of all the basis states. So in this case, what we want to basically prepare is this state. So like a superposition of, the 0 states of all the qubits, the first qubit being 1 and the other ones being 0, the second qubit being 1 and all the other ones being 0, the third qubit being 1 and all the other ones being 0, and then finally the last qubit being 1 and all the other ones being 0. So, in order to prepare this state, they, recommend using this sort of, little mini algorithm in itself. So define RK to be this little single qubit guy, and define T to be this little 2 qubit guy. And if you have K control qubits and they start in the 0, 0, 0, 0, 0 state, what you do is you can get this state here by applying RK to the first qubit, and then the TKJs to adjacent qubits along the line. So again, R on the first one, and then just sort of go along the line, a T on these two, then T on the next one, T on the next one, da, da, da. Like, don't go, apply to these two and then apply to the next two. Like, actually, like these two, and then like these two, and then like these two, like, da, 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 da. Okay. And if you do that, you'll get this state. So that's cool. So you get a superposition, of all the qubits being up or just one of the qubits being down. Again, this, kind of juggling back and forth between those two notations, right? 0 is up, 1 is down. Okay, so let's just call that whole state preparation for our control qubits UK. So we have our K control qubits prepared. So in line with like this sort of permutation generating procedure we talked about before, like think about this in the context of you've already symmetrized K qubits and you want to symmetrize an additional K+1 qubit. You prepare K control qubits to help you do this. And then you apply K Fredkin gates, K controlled swap gates. If J runs from 1 to K, then the jth Fredkin uses the jth control qubit to condition the swapping of the jth and the K+1 qubits. We'll see a picture, okay? Yes, whatever that means, right? So you do that, and then, as before, we do the Hadamard, then the inverse of the Hadamard, which is the Hadamard QFT, then, inverse. Here, we apply the inverse of UK, the preparation for the control. Then the idea is you sort of cascade this construction for all the Ks. So, you start with K equals 1, where we've like already symmetrized 1 qubit, trivial. And then we want to symmetrize it with like the next one. So we introduced K equals 1 control qubits, prepare them, do the Fredkin, unprepared. Then move on to K equals 2, add 2 more control qubits, prepare them, do the Fredkins, unprepare, da 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 da. So you keep doing that, and in the end, you're going to need n times n-1/2 control qubits. So like for n equals 4, you're going to need 6 control qubits total. Finally, you measure all the control qubits, and if they're all in the 0/up state, then our qubits will have been symmetrized. So it's like sort of easier to see like in like the diagram. So, here's the case, this is like from their paper, where, you have 4 qubits that you want to symmetrize, and then here's the 6 controls. So we, iterate over K equals 1, 2, 3, and these are the unitary preparations of the controls. So, like this one, if you unpack this, right, it's just that, whatever, what was it? Just the R, I called it R. This is the R gate, right? This one's gonna be like an R and then like one of those T guys, because there's like just 2. This one's gonna be like the R and then like a T guy on these 2 and then a T guy on these 2. And then we do the controlled swaps. And so that's this notation, right? So it's like control on this, and then this like swaps these 2. And so, and like you see the beauty of it here, right? So that it's like, just consider like the 3rd round, like right here. the first 3 qubits have like already been symmetrized, basically. I mean, so to speak, right? Like we actually haven't done the measurement yet, okay? But like basically, they've already been set up. So then, you know, all we need to do is swap each of these 3 guys who've already been dealt with the new guy, right? So this just swaps this guy with the new guy, this guy with the new guy, this guy with the new guy. So, you know, again, we start off with just like the one guy. And so we basically prepare to symmetrize it with the second guy. And then, you know, we got these 2 guys. These 2 are already symmetrized. So then we just have to swap, you know, sort of control swap with the new guy on the block. And then these 3 are already prepped. And then you symmetrize with the 4th guy on the block. So, you know, that should be like, now it should be intuitive what all this blah, 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 you know, indices are really saying here. And then you apply the inverse of the preparations on the controls, and then do your measurements. So again, here's just sort of a direct translation of that into Q-tip code. And you know, if you actually like read this, you will observe that you know, in the paper, I just follow the notation in the paper above, and you know, they start counting from 1, but you know, as a computer programmer, of course, you always start counting from 0, and so you know, all the indices are off and whatever. So okay, here's our U, here's our T. Build that. Okay, we're gonna do 4 qubits. We're gonna need, you know, this many controls, 6, and generate some random qubits to use. Tensor, you know, P, or that's, you know, the number of controls we need. P controls to the qubits. And then there's just this sort of just does the thing. So we just go over K. We start, like I try to like mimic this where we sort of start counting, you know, if these are labeled, you know, 0, 1, 2, da, 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 we start, you know, with this control and then these, right? So I start counting like backwards basically. So that's what this little offset guy is just keeping track of. You could do it a different way, obviously. And we get a UK that just like acts on, you know, the first of this round of control qubits. We apply the T's to the controls like in a line that are relevant in this round. That forms the unitary preparation for this round. Apply it to the state. Then we do the Fredkin, you know, using our controls to swap the jth and the kth qubits, and then apply the adjoint of the preparation. And then finally, you know, project all the qubits into the 0 state, all the control qubits into the 0 state, take the partial trace, and then, you know, symmetrize the qubits in the classical way and compare them. And so, see, get the right answer. And, you know, if you're like concerned, you know, what n equals 2, okay. 1 control qubit for 2 qubits, et cetera, et cetera, et cetera. Okay. So that's the word. So now let's see how to like actually do this, you know, for real. And have we gotten results, by the way? Yeah, on one of them. Okay, we'll come back to that. Okay, so we're gonna use, and you know, I set it up this way because I always like to implement everything sort of like by hand with something like Q-tip or even just NumPy, which arguably is like a little bit crazy. I mean, you know, because you gotta like make sure to tensor identities with everything, and you know, it can get a little bit painful, obviously. But you know, in my experience, sometimes certain things are obvious only if you're really eyeballing the matrices that you're using. So, I always like to like sketch it out in Qtip first and then move over to Qiskit or something. So, you know, one thing, everyone's got a different convention. So, I mean, for whatever reason, they gave a reason. I forget what maybe it was a good reason. Qiskit, it's if you tell it to take the tensor product of A and B, it does it like B tensor A. So basically, like you'll notice in the code, like all of the indices like are swapped. Okay, so just be aware of that. So what we're gonna do is we're gonna prepare a you know, symmetric multi-qubit state. We're actually gonna start with, you know, we're gonna generate a spin J state. We're gonna find its stars. We're gonna, you know, then prepare a bunch of qubits whose rotation axes are pointed in those directions. And then we're gonna like construct this whole circuit. It's gonna prepare the symmetric state on the quantum computer. But then, you know, the question arises like what are we gonna do with it? You know what I mean? Or, you know, okay, like, so just to make sure it works, and, you know, as just sort of like a nice digression, you know, Qiskit has a cool little, you know, tomography feature. So you can do, I mean, it's kind of interesting that that word caught on. You know what I mean? You're just sort of diagnosing basically a quantum state, right? So tomography, you know, if you're not familiar with that term, is just basically given a quantum system, in fact, many copies of a quantum system, you do a bunch of measurements and try to reconstruct what quantum state was that. And you can do tomography for states, for processes, and they have, you know, some nice built-in stuff for dealing with that. So you can basically generate a bunch of, like, given a quantum circuit, generate like a bunch of circuits that do tomography on that state, or even just a subset of that state, which is in fact what we're gonna do. And then they even have like a built-in like fitter class that you basically give it, you know, the results of the measurement, and it tries and like recovers like the density matrix. And in fact, you know, we're gonna sort of do a little thing, you know, they reference this in the documentation. So we're not just gonna use the tomography to recover like the state of all the qubits, but we specifically wanna try to recover the state of the you know, the qubits we symmetrized, which indeed means we have to condition or post-select on all the controls being in the 0 state. And so, you know, gotta hack it a little bit to do that. So we'll see. So, so yeah, you know, import some stuff. Okay, here's our, you know, famous little linear map from the spin J's to the 2J symmetrized qubits and back, which we're going to use to test it up, to test things. Here are some functions which convert from XYZ coordinates to spherical coordinates, which we're going to use. It's going to come up using the physicist convention. Phi runs from 0 to 2 pi, theta runs from 0 to pi. Keep that in mind. Here's our UK and our TKJ, and what I've done here is, you see, I've turned them into operators that Qiskit can understand. So basically, you can make your own operator by just sort of wrapping a NumPy array in this sort of operator class. So we set a J value for spin to start with. So, you know, for J equals 2, we're going to have 4 stars or 4 qubits. And just to start, let's do it locally using their QASM simulator. Okay. You know, and then, you know, so basically at the beginning of this whole affair, I basically ran it with spin, sorry, J equals 1, so, you know, 2 qubits on this quantum computer, and then I ran it for spin 2 on this quantum computer. And so with bated breath. I'm sure you're waiting for the results of that experiment. But you could also run it on, their fancy classical simulator, which is pretty useful to have. Okay, so all right, so J equals 2. D is the dimensionality of the spin, 2J plus 1. N is the number of qubits, 2J. And P is the number of control qubits we're going to need. We start off generating a random spin state, random spin J state. Find its stars, using my favorite function that I ever wrote, spin to X, Y, Z. And then convert those X, Y, Z coordinates into spherical coordinates. Now, I mean, we could just probably have extracted it directly into spherical coordinates, but whatever. Okay, so the way that Qiskit works is, you start with a little quantum circuit, P plus N qubits. Okay, so now we got to load in our qubits. So, I mean, this is why I found like the spherical coordinates of the XYZ points, because we can, all the qubits start in the up state. So, we do like a rotation around the y-axis, and then a rotation around the z-axis, and then the rotation axis, the expected rotation axis of the spin is going to be pointed in the desired direction. So we prepare all our qubits by rotating them all by these angles. Then here is our little symmetrization algorithm. It's just basically the same thing as before. So we just iterate over K. We have this offset thing I was explaining. Apply U, and then apply the TJs along the line. Apply the Fredkin, and actually, you may have noticed that this actually iterates backwards. It actually doesn't matter if you do it forward or backwards, but this just like makes a prettier picture, as we'll see. And then we sort of undo the preparation of the controls. So go along the line in reverse. Apply the adjoint of the T's, and then apply the adjoint of the U on the first one of this round. And then we can look at it. So maybe we'll just look at it right now. So let's look at it for 1 first. Okay. So for spin 1, there's 2 qubits. So here's the 2 qubits. Here's the Y and the Z rotations that prepare them in the right state. On the control, we prepare it by just applying that little R guy. Oh yeah, I noticed actually. Yeah, I should fix that. I called this guy R, but then I called it U here. Please don't be confused. Should change that for consistency's sake. Okay, apply that, whatever you want to call it, and then apply the Fredkin gate. And they got this nice little visual representation of the Fredkin there, and then apply the inverse. So you get that. Compare with, let's do it for spin 3 halves. Spin 3 halves got 3 stars in the sky, 3 qubits. So here's our 3 qubits, preparing them, and then we have 3 controls. So, here, think about, so round 1 applies to Q2 here. So we prepare Q2 with this little unitary, and then here's the controlled swap, and then here's like the inverse unitary. And then round 2 involves qubit 0 and 1. Prepare them with the unitary on the first guy, and then the other unitary on those 2. This is like the R/U, and this is the T. And then we do the controlled swap, which, qubit 3 and 4 are already, quote unquote, symmetrized. So then we just have to take each of those in turn and, do the same kind of swapping thing with the new guy in town, this guy, the third guy.
I just have to check the Fredkin gate is unitary also, isn't it?
Yes.
Okay.
And then, unwind it, apply the inverse of the preparation. So, keep looking at it. So spin 2 is, precisely the case which was, imaged in the paper. And so we've basically reproduced our diagram here. Prepare the 4 guys. And now you see, here's round 1, qubit 5, apply the unitary, control, inverse unitary. Round 2 involves qubits 3 and 4, unitary, here's the T, then these 2 controls, and then like undo it. But then, round 3, comes into play here. We have 2 T's involved, right? This T on the first 2, and then this T on the second and the third. And, we can't even fit it onto the screen. It's so long. Oh my God. I have to say, so what is this? 9 qubits or 10 qubits? How much was, okay, I think I ran spin 5 over 2. Yeah, because so for spin 5 over 2, you got 5 qubits, 10 control qubits, which is 15 in total, right? And so, I'm looking and I'm saying to myself, oh yeah, well, they got this 15 qubit quantum computer, this Melbourne, or maybe it's 16, whatever, who cares? Point is, it worked terribly. I have to say, I mean, this is something like really to keep in mind. The quantum computers, worked pretty well for, just symmetrizing, 2 qubits, like 3 qubits, like whatever. But, you look at this gate, I mean, this whole circuit, right? And it's just like, this is like quite a lot of operations, and it goes on and on, right? And in fact, you're preparing like a symmetrized state of a bunch of qubits, which are also like entangled with these controls. So there's like entanglement all over the place. You got a lot of gates. I'll tell you, this thing basically takes the trace between, the actual thing that you calculated and the expected. Should be 1. I literally did it last night, and this was like 0.05, which is just embarrassing. I mean, come on. But it's good to keep in mind, right? It's just like we're still at the noisy stage. Things are not necessarily going to work well, especially if they're complicated. Okay, so on to the tomography part, right? We want to kind of be able to like reconstruct, we like prepare this multi-qubit state, but then we want to like reconstruct that state by doing a bunch of different measurements. So there's a whole theory of like what are the most efficient measurements to do in a given context to like reconstruct the state. And that's not a theory that we will be talking about right now because it's sort of complicated. But we will just be using Qiskit's built-in thing. But even that, has some like little footnotes that are worth mentioning. So basically here, if you want to do this at home, here's what you do. They got this nice little function, state tomography circuits. You give it a circuit, here's our circuit. And you also tell it like what qubits that you care about. And so in this case, we don't care about the control qubits, we just care about the qubits that we're symmetrizing. And then so this, is like a bunch of circuits. How many? Let's find out. In this case, oh, it's still calculating. Okay, whatever, it's busy. Come back to that. It's a bunch of circuits, is my point. So then we copy them all because we're going to use them later. So then we create oh, look, it did it. Okay, come back, going down here. 243 circuits to do tomography in this case. 15 qubits. Trying to do tomography on 5 of them. over 200 circuits, each of which you want to run many, many times. So, just to give a sense of the scale. Okay, so we've generated these circuits. Now what we want to do is add in like the measurements on the control qubits to our tomography circuits. So we create, a bunch of classical registers for each of the controls. And we add those classical registers to each of the tomography circuits in turn, and then like add in a little instruction to measure, that control qubit, put the result in that classical register. Okay, so then you're ready to run it. Now, and here's like another useful thing to know, like if you're working with this IBM thing, because like, as we just saw, you want to run like 250 fucking circuits, so what they do is, well, I should say first, if you just want to run it locally, right, you can use their little AIR backend, the QASM simulator. So you just basically get this backend, call this function execute, and give it this like list of the circuits, tell it how many shots you want to do each circuit for, and then, get the results. If you want to, connect to the cloud, then, use this little IBM Q widget that you import, load the account, and then it's really useful to use a job manager, which basically, so what this does is you take all the circuits, you kind of optimize them using this little transpile thing. And what it does is it like takes all your circuits and it just sort of like bundles them up into, however many circuits can be handled like at a time. So it like divides it up into like several jobs and then like sends each job to the quantum computer. And so like you don't have to like take, care of all that like separately. You can just sort of have this do it for you. So it's good to know. And then you get the jobs back, and the results are sort of, they're kind of like, as I say, bundled up. So then you kind of want to call this function combine results. So then the results will be in the same format as like we got up here. So, right. Now we got to implement our post selection, right? So we only want to reconstruct, the density matrix of the symmetrized qubits, but specifically on the condition that the controls were all measured to be up or in the 0 state. So you figure at some point they're probably going to have a kind of, easier way to do this, but whatever, this is what they said to do. And it's not that bad. Basically, you copy the results, okay, and then iterate all like over them all. And then for each one, you get like the counts, okay, which is like a dictionary of where like the keys are like the results of in the classical registers, which like, we have the classical registers associated with the 4 qubits, and then the classical registers associated with the controls, and those are gonna be separated by a space. And and you get, so it's like a bunch of ones and zeros. So it's basically the format, like 1 1 1 1, and then space, and then whatever, how many it would be in that case, 6 or something control qubits. So okay, sorry, get a little into the details here. So basically what this does is we basically want to throw out the classical registers associated with the control qubits. So this basically readjusts the the thing that keeps track of the classical register sizes, hack the labels, change like the number of memory slots. Then we go over this dictionary of counts, and as I say, basically the results of the control registers and the other registers are separated by a space. And so we just look at the first grouping of ones and zeros, which are the controls, and we look at the case where all of the answers were 0, and then we just like, you know, use only those. So like keep track of those and then replace the data with that. Okay, sorry, I don't know. I don't know if it's helpful to like go over it in exactly that level of excruciating detail, but I have to say, you know, they said basically to do this in the tutorial. I was like looking at this code, I was like, man, I don't know what this is doing. So, you know, it's like I like, you know, had to go through all these things. I was like, so what is this? You know, like see reg sizes, like whatever. And basically, I just thought it might be, if you want to do this yourself, worth sort of seeing how these internals function. I mean, basically, it's like you have all the data and you want to go through the data and pretend that there were never any controls. But like specifically, you also want to look at in the data, you want to save the data only when the controls were all in the 0 state. So that's what you do. Because you want like this whole little bundle of results to be in this like format, so you can send it to their state tomography fitter class. So this takes the data, and then it takes, so okay, like remember back here, they we generated the tomography circuits, made a copy of them, put that to the side, and then, you know, we added these like measurements of the controls. So now we like come back and, you know, give this tomography fitter the copies of the tomography circuits. So like without those measurements. And then we call this fit function and it generates row. Boom. Okay. So now we have our density matrix that we've reconstructed of like just the permutation symmetric qubits, which we've gotten because precisely we conditioned on the control qubits all being up. So now what we want to do is compare it to what we started out with. So we generate this linear map that takes us from, you know, the spins to the symmetrized qubits. We know what the density matrix should be because, you know, way back when this whole story started with just generating the spin state. And then we found the stars and then found the angles and da. So we have this. So, you know, we just like take the outer product of it with itself to get the density matrix. And then we take this density matrix, which again is like 2 to the n dimensions where, you know, n is the number of qubits or whatever, 2 to the 2j. And so we like downgrade that symmetrized qubit density matrix to a spin density matrix. And then we take the trace between the correct row and our row. And we print the answer. So, you know, you get pretty good results. So like, let's say we want to do 2, we're running it locally. Here's the circuit. It thinks about it for a second. And yeah, there you go, 0.98. Cool, very cool, right? So then, okay, so we may as well run it on, you know, just for the sake of argument, like, dare we even do j equals 3? How many is that, right? It's like, so you have 6 qubits, and then 5 times 6, 15 controls. 21, was that 21 qubits total? Why not? They say they can do up to 32. So there you go, let's do it. Bam. Look at this circuit, endless. This is like a novel. This is like a novel length quantum circuit right here. Endless, endless fun. Boom, boom. Oh, look at all that. It's great. It's great. Oh, it just keeps going. It never ends. It's great. I love it. Okay. So anyway, So then, you can go on their little thing here, right? It's like the internal pane for the quantum stuff. And you can look at your jobs that are running. So you can see that, that was quite a lot of stuff, or like whatever, quite a lot of circuits. So they bundled it up into 3 jobs just sort of seamlessly. And so you see them here, and look, they're already running. Love it. Here, you can see here, these 3 jobs were run an hour ago. Indeed, it's 5:15. So let's check those out. These were actually run on the quantum computer. So which one's which? Okay, so on IBM Q Athens, which is just like a 5-qubit machine, we ran this simple little circuit, which symmetrized 2 qubits. And what did we get as an answer? 0.81-ish. It's okay. I mean, it's not that great, It would be better if we could run more shots, right? Like when I run it locally, I did 10,000 shots. Okay, I mean, we did here, the simulator and the quantum computers max out at this number of shots, about 8,000 shots. So, I mean, doing 2,000 more, I guess, is like somewhat significant. But yeah, it just goes to show that, I mean, like, obviously we just ran it more times, we could like get that number up to 1. But yeah, just like be aware, noisy, intermediate, quantum, whatever era, stuff doesn't always happen the way you want. And just to make that point, to drive that point home even further, where is it? Okay, then we ran, I ran, I think it was a spin 2 guy, so 4 qubits on their Melbourne quantum computer. And, that involved like 10 qubits, basically. And then you look and you're like, oh my God, we got the answer 0.0857. It's horrible. It's terrible. But you might wonder, shit, Matt, does your code not work? Is this your fault? I submit to you not, because when you run it on the classical simulator, it works just fine. At some point, that will appear here. In fact, I'm a little worried about it. Where is it? Because it looks like here, you see the jobs are done 3 whole minutes ago. Sometimes these Jupyter notebooks get a little
Matt,
fussy. Yes.
I would suggest to avoid this kind of issues, you might try to run your Python notebook within IBM Q Experience. You can just upload it there and run it from there.
Yeah, that's a great point. I haven't actually done it. Oh, here it is. It just came out.
Okay, yeah, it came back.
But yeah, it's like a little stressful sometimes, especially as you're working on a Jupyter notebook and things are changing. And
yeah, because this seems to be more the API kind of issues, timing on your computer, their computer, time zones, and things like this.
Yeah, I get this warning a lot, pretty consistently, for whatever reason, about timestamps. But yeah, that's a good point. I haven't actually worked with the IBM Experience, like their internal notebook thing. I'll have to check that out. But yeah, you see here, we did it with quite an enormous number of qubits, whatever it was, whatever we calculated, 21. And, it should give the right answer, basically. There you go. Would a totally random answer be 1/16? You're saying because, this is a question from Jamie, because there were 16 qubits, you mean? I don't know. I mean, yeah, what would be a totally random answer? I guess in theory, if the dimensionality is high, a totally random answer should be close to 0, right? Because if, any two vectors in increasingly high dimensional space are like likely to be orthogonal. So maybe that's an answer. It would be interesting to see, one thing I was thinking about is like, I didn't actually visualize the stars on the sphere, which I could have done. And, I was like, well, you could look at the sphere that you start off with, the constellation or whatever you start off with, and then the constellation you end with, which admittedly seems to be like in a mixed state, although it should be in a pure state. You wonder, like, from the way the constellation is distorted with different kinds of errors, different kinds of noise in the quantum computer sort of change the geometry of the constellation in different ways. I have no idea. But actually, that's a good segue into actually like why these authors sort of worked on this algorithm to begin with. So, great little paper here, some of the usual suspects and coming up with great quantum algorithms. Yeah, so I'd love to know, and maybe Vesseline, maybe the answer to this question. If anyone like uses this sort of like stabilization algorithm for quantum computers. So basically what their idea is to say like, okay, you're doing your quantum experiment and there's like noise and you're probably running your experiment many times. Well, what if you could run like a bunch of copies of your experiment, like in parallel? So you got like these qubits, these qubits, these qubits, these qubits, like all doing the same experiment. Well, it's like supposed to be the same experiment. The same thing is supposed to be happening in each case. So it shouldn't make any difference, like if you symmetrized across all the experiments, right? So then they're like, all right, so, you have the experiment unfolding. Every, like microsecond or like whatever, project the whole thing into the symmetrized subspace of like all the qubits. And, or at the very least, like symmetrize across the states of each experiment. And, if you do it rapidly enough, you have like the sort of the quantum Zeno effect. In other words, you might be like, oh, well, you do the measurement of the control and then, sometimes it's symmetric, sometimes it's anti-symmetric, sometimes it's like mixed signature, like whatever. But, if you just, you project it and then you get the symmetrized state and then just like keep projecting it, like keep measuring it like rapidly enough, the probability of you getting something like not the symmetric state is like very low. A watched quantum pot never boils, as they say. So basically, they're like, yeah, potentially there's errors. And the errors are affecting the different instances of the experiment in like an asymmetric way. But they're all supposed to be, the same experiment. So you like project all the experiments into the symmetric subspace, and then you'd be able to kind of correct some errors that way. And I'd love to know if anyone actually does this. It's from 1997. I mean, I imagine that, there's like, in general, we have so few qubits that, I mean, it's a sort of challenge to be, this would be more fun if, you had like, enough qubits to like run the same experiment in parallel, like in the same quantum computer. Maybe, the people get to play with the big quantum computers, do this kind of thing. But in any case, yeah, Jamie says, yeah, what's the deal with the Melbourne? Now, apparently, you go on this thing and it'll tell you a little bit about, the, the error rate. But I'm not gonna lie, I don't actually know how to interpret this. I gotta read more about it. So anyway.
So yeah, Matt, could you pull that screen back up with the error rates?
Yeah.
So like, yeah, I would not expect this to like run really well on a real device yet. Just because like if you look at the CNOT error rate, your 2-qubit error rates are going to be, if I'm reading that right, I think that means that basically your CNOT is going to work like 95% of the time, which is about par for the course right now with the superconductors. And then your single qubit error rate is much better. It's going to work 99.8% of the time. So I think a lot of times, like even just one CNOT, it's actually going to compile better if you like decompose a CNOT into like multiple single qubit gates. So I just think there's just so much going on with that algorithm that's going to run a lot better on a simulator. So you don't need that many qubits. So you just need to do a lot of operations. So that simulator is going to work really well, but I think you're just doing too many operations for it to work well on a real device. I think we would need error correction. So yeah, I think we would just need either more qubits or higher fidelity qubits. So I think that's what's going on, but I'd have to look at it closer to figure it out.
Yeah, for sure. Thanks for that. Yeah, I should try it on a couple different systems. Like I should, maybe I'll do that before next week. I'll give it a try on like Rigetti's, and maybe, I've never actually worked with ion Qs. And it would be interesting to compare if like anyone or any of these are like actually able to get a good result for, actually symmetrizing more than 3 or 4 qubits.
Yeah, I mean, IonQ has better fidelity, so you might get the best results on that. But again, I think there's just so much going on. I don't know if anybody could get that to run really well on a real device right now.
Sure.
I think we would need, like I said, either better qubits or more of them, and eventually we would get it. But right now, I think the simulator would be the way to go for this one. But yeah, it'd be cool to like try it out and see what happens.
Yeah, definitely. Oh yeah, well, while we're on this page, it's interesting to look at like the fluctuations in the number of jobs like that are in these queues. Like I have to say, it's in, like I don't know. I feel like there's certain times or times of the day where, like for example, last night I was preparing for all this, right? And like Santiago, Athens, Vigo, all these like 5-qubit ones were all like 600 jobs. And then like Melbourne had like 20. But today, the numbers have completely flipped. Now it's Melbourne that has like 500 jobs, and all these guys are like 20, 30. It's just sort of interesting, I'd like to see like one of those like, kind of like a graph of like the usage statistics based on time of day and maybe even geographical location of, wherever these requests are coming from. But, even if they can't handle such a big circuit, nevertheless, I am so thankful for them to have put these things online for free. It's so great. So yeah, I recommend, these were the 2 references, basically. Like this was like the original paper I found. It's all right. But it was through them that I found this, paper from the 90s I'm talking about. And I'll admit it was behind a paywall, and I put it online for you guys to download. Shh, don't tell anybody. So yeah, that's pretty much what I had to say. Actually, well, there's maybe one more thing I was thinking about that is sort of vaguely interesting. Obviously because there's a measurement in this algorithm, it's not like reversible, right? But you might wonder like, okay, like what if I wanted to keep that reversibility? I could have my controls, prepare my permutation symmetric state, and then like maybe I play around with permutation symmetric state, you know, apply some gates that preserve the permutation symmetry, but like never actually measure the controls. You know, in theory, right, like you're applying these gates to the qubits, which are kind of in a superposition of like being symmetrized and not being symmetrized. Well, you know, to use the language of many worlds, you're sort of acting on, you know, each of those worlds or possibilities in parallel. So then in theory, you know, if you never measure the control, you do some stuff to the symmetrized qubits and then apply the inverse of the whole preparation algorithm, then what? I naively would have said, well, you just end up back with a bunch of separable qubits, but, you know, the stars would be pointing in different directions, and you get exactly the same thing as if you just started with the spin and like applied a unitary to that. But actually, when I did that little experiment, that's like not exactly what happened. In other words, when you would do the inverse, you'd actually end up with qubits in you know, various states of entanglement, which in a way makes sense, right? Because there's like a one-to-one map from the separable qubits to the symmetrized qubits. But like, what if you apply that algorithm to some qubits that like already like a little bit entangled? You know, then it's kind of like a, you know, many-to-one map, basically. And so in theory, though, it's almost like a gauge redundancy in a way. Like in theory, there should be some operation I can apply that would take these qubits that are in some state of entanglement and sort of uniquely map them to the right separable states, which, if you apply this algorithm, will take you to that permutation symmetric state that you started with. But you know, I don't know exactly how you would, or how to construct that. But yeah, like in theory, right? It's like you could just like not measure the controls, like do some stuff, and then, you know, measure the control later. It just seems like there, you know, like a lot of different kinds of things you can play around with. But yeah, with that, you know, that's pretty much the story. Any other questions or concerns?
I would just add my ignorant 2 cents. You know, once you have an entangled state, the only way to disentangle it is by measuring it. The only way to entangle it is through decoherence, and then you've destroyed reversibility. You've destroyed the unitarity.
So, I mean, if you apply the inverse of the unitary, you know, start with a separable state, entangle it, you can like disentangle it with a unitary operation. But yeah, certainly if you measure it, it's going to break it. And then, of course, as you know, it's going to make it.
You say you can disentangle it with a unitary gate?
Yeah, I mean, it stands to reason, right? It's like if you take a unitary and then multiply by its adjoint, you just get the identity matrix. So.
But again, once you make a measurement, all bets are off.
Yeah.
Once you make a measurement, you've destroyed unitarity.
Yes, unless, of course, you can apply unitary operation to the measuring device itself and also all of the humans who perceived the result and then reverse the whole thing, then you could reverse the measurement, I guess. But that's a long way off.
Je ne sais pas.
Yeah, that's for the 23rd century. Well, you know, I hope everyone has a good Halloween. We've seen a way of sort of using these, to the extent that this algorithm is spooky, you know, it's like, obviously involves entanglement, but also this kind of crazy thing, right? It's just, I never, my childlike joy never diminishes when I'm able to do something like, I'm going to put these two qubits in a superposition of being swapped and not swapped, simultaneously. I just like that. And, thinking about like the interpretation of quantum mechanics, my personal favorite one, which, kind of is like a generalization of the relativity principle. It's like, the way that we should think about this is like, we have, this exact control over this system. We have this control qubit, we have these two other qubits, and then we do this unitary operation so that whether these two qubits are swapped or not depends, sure, on the control, whether the control is up or down, and nothing else, right? Like the fact, are they swapped or not? It doesn't depend on the air molecules. It doesn't depend on like all this other stuff, all the whole noisy jumble of the world. We've isolated the thing so sufficiently that like the fact, are these swapped or not, depends on only one thing in the entire universe, which is just that control qubit. And that control qubit's in a superposition. And so the whole thing, the three qubits, are able to be in a superposition of being swapped and not, because the fact of whether it's swapped or not is only relative to that control. But then of course when we measure it, it becomes defined relative to us, and largely speaking, the public world, right? And that's definitely, that general way of thinking is my favorite sort of paradigm for thinking about quantum mechanics. And it's kind of like, there's some nice papers by Carlo Rovelli where he developed a sort of, relational relational interpretation of quantum mechanics. And it's not unlike the Everett sort of relative state idea as well. But, emphasizing this sort of like, there are no just purely objective public facts. Facts are always defined relative to things. Facts consist not in like, facts are relationships between things. And if something, whether it's this way or that way, is like not defined by its relationship to like anything but this other guy, that's what quantum computing is all about. It entirely depends on your ability to prevent facts from leaking out into the world, but sort of segregating them in these little areas so that whether something is defined or not relative to so-and-so can be manipulated and controlled. So just a little philosophical reflection for you there.
So Matt, do you believe in Everett's many worlds? You talk about it a lot.
I think that in many instances, it's like a great way of developing intuition. But again, it just seems to me that, like in general,
I mean, is it real? Like yeah.
The footnote is like, what is a world? Is itself relative or like dependent? Like, in other words, like I have a vector, right? Like I can break it down in like any number of bases. And, what? Those, and those are supposed to be the possible worlds, right? Given like a measurement, that gives me a complete set of eigenvectors, and I expand my state vector in terms of those eigenvectors, and then like each one's supposed to be a world. But like, if I'd measured a different operator, I would have decomposed the world into a bunch of different possible worlds. So I think, my one thing is like, I feel like when people say possible worlds, people imagine like the classic Star Trek notion of like a parallel universe. And just in the same way that like quantum teleportation is like not like Star Trek teleportation, like the many worlds of quantum mechanics is like not like the parallel universes that we see on TV. So, like with that caveat, like I'm sympathetic to the.
So it's a mathematical construction. It's not reality, which is a difference. I mean, there are not.
You can come
there
up
are
with a
not
better
an
way of saying these
Yeah.
two qubits are in a superposition of being swapped and not being swapped. If you can come up with a better way of saying that, then be my guest. You know what I mean? I think it's like that grammar seems to work for us. You know what I mean? Like when I say that, you're like, okay, like that's crazy, but like I kind of know what you're saying, right? At the
I mean,
very
are
least,
there
it's a useful way that we humans have of like telling a story about
are
what's
there an infinite number of the presentations that you just gave? Or is there just one in reality?
So
Well,
I
I
agree
think
that when you start thinking like this, you have a lot of headache.
Yeah,
Uh,
right.
But if you think, for example, when we had the circle and its combination of up and down, representing the state on the circle, I mean, one is the vertical and one is down, I mean, right? Basically, the superposition is actually the horizontal one that's equally distance from both. And then you say that it's superposition because when you do a measurements, you find it equal amounts being in one or the other. But it's completely a different state from both, right? It's a question of what is your measurement doing and what is the state of the system.
Yeah, I always find like the thinking about, you know, probabilities and also many worlds in, you know, without confronting like the geometrical aspects like that are often happening, you know, it is like a perfect recipe for a headache. Like, as you say, you know,
Yeah.
a superposition of up and down is just pointing to the right, basically. And, you know, to call it a superposition is like relative to a certain experiment that you're doing, a certain way of like dividing up the world. Yeah, so you just hand someone a state vector and, you know, ask for an interpretation of it in terms of probabilities, ignoring, you know, the way different kinds of geometrical and physical symmetries are encoded in it. It's not going to work. Well, if there's no other comments, maybe we'll call it an evening.
Okay. Yep.
Okay. Thanks, Matt.
So long.
Bye.